Hey guys, welcome to my transport crash course, which is going through the past paper exam 1, most of the questions. So these are the ones I went through in the actual crash course, but due to my technical incompetency, I couldn't figure out how to set up the recording on the day, so I'm just going to do it now. So yeah, hopefully this is helpful, but disclaimer. Actually, I don't know what I'm disclaiming, but yeah. And I know I look cooked, but it's fine. Okay, so hopefully you know by now, but the topics are split up into part 1, which is like week 1 to 5, and then part 2, which is week 7 to 10. So in part 1 to 5, that was like calculating how many cars are going through one point and stuff like that, and that came under traffic flow theory. And then green shield equation was like the graphs like this, which we'll do a question on today. And then the 4-step model had trip generation, trip distribution, mode split, and trip assignment. And then part 2, the first week, or like week 7, was intro to road design, which is like the stopping sight distance questions, where the question is just based on stopping sight distance, not the curvature of the road. And then like overtaking distance calculation and kinematics, like force questions. And then we have horizontal alignment, which is drawing when the road is curved like this, so designing for this kind of curve. And this is the top of the car. Whereas vertical alignment is calculating when the road is dipping up and down, so like this view. And then Earthworks is like if you have like a terrain, what cut can you take such that you minimize the cut and fill amount. It's very similar to 3101 if you did that, or maybe it's 2101. Okay. So I'll start with the Green-Shields equation. Green-Shields equation questions. So it says the speed and density data was collected like this, but with this specific data set, they gave us like a speed range like this, right? So we don't have like a specific speed for these frequencies. So what we're going to do is actually just take the middle number of each speed range and just kind of use that as like the average speed value that we're going to use to calculate stuff. So I'll just write here. So that would be like 5, 15, 25, 35, etc. So just taking the middle number like that. And for future reference, what we're going to need is the average speed. So if I calculate that, that would be taking the middle of these numbers, which would be 40. And I'm also going to find the average density, which from using this column, that should give me 60 as well. Okay, so question I says, sketch the relationship between the different elements of traffic flow theory and mark those features. So firstly, sketch the relationship between different elements of traffic flow theory. Okay, so what that means is the different elements of traffic flow theory, that's speed, density, and flow. So they want us to sketch these 3 graphs basically. So we've got the speed density graph, which is like a line with negative gradient, speed flow graph, which is like a sideways parabola, and then flow density graph, which is like upside down parabola. And then in the lecture slides, you'll find that there's like some formulas for these as well, like this. But actually what I like to think of them is just like, they're literally just like fancy ways of saying like equation of a line. For this one, equation of a sideways parabola, and equation of a parabola. So as I will show you in a second, I like to just use normal equation of a line and parabola to find the equation for these ones. So firstly, let's try and sketch speed density graph, right? So that should be speed on the y-axis and density on the x-axis. So again, like since this is a line with negative gradient, I'm basically just going to treat this as a line with equation y equals mx plus c. And the line should look like this, right? So one information that we can know actually is the minimum and maximum speeds. So since the speed ranges from 0 to 80, that's going to be my range values here. Like that. So if this value here is 80, that's equivalent to the y-intercept of this line, right? So if you have a y-intercept, that's going to be like what the value of c is. So it'd be like this. Y equals mx plus 80. Now, how do I find m, the value of m? So either you can like take 2 points of a line, or what I'm going to do in this case is sub in a point. So we don't know the value of this point yet, but what point we can sub in is the average values we found here. So I'm going to use average speed equals 40 and density, which is k, equals 60. And then so subbing those in, I get y, sorry, and since speed is v and density is k, this is equivalent to saying when y equals 40, x equals 60. So 40 equals m times 60 plus 80, and that should give me m equals minus 2/3. So then that means my actual equation of this line is minus 2/3 x plus 80, which makes sense because the line has a negative gradient and it has a y-intercept of 80. So, and this form is basically equivalent to writing it using this. Oops, that's okay. So that's like the proper form, but it's equivalent to using the equation of this line. Okay, and then it says, okay, so now I'm going to try and find what the value of this point here is. So what I'm going to do is, since I have the equation of my line, I'm going to sub in when y equals 0, x equals, and then I'm going to sub that in order to find the value of x. Like that. So that means this x-intercept is 120. And then, actually I can label these points now. So these are special points. This x-intercept here is going to be the maximum density possible. So this is going to be named jam density. And then this value here, that's the maximum speed you can do and with 0 density. So if there's like no cars on the road, what's the maximum speed you can go? That's going to be 80 k's an hour. So I'm going to call that free flow speed. So that means jam density is 120 vehicles per kilometer, and free flow is 80 kilometers per hour. Okay. Yeah, sorry, my brain's a bit slow today actually, because I'm tired. That was going to be my disclaimer, I just forgot it. But yeah. Okay, so then that's my speed density graph, and now I'm going to basically just draw the other two graphs, so speed flow and flow density. And all I have to do is draw the parabola for those, and I actually have all the values I need now. So this one is speed flow and flow density. So remember our speed ranged from 0 to 80, so I can label that right away. And our density ranged from 0 to 120. which I can fill in there. And then now I want to find my peak flow. So how can I find that? I'm going to find that using Q equals VK, which I'm sure you're familiar with now, hopefully. So in order to find flow, I'm going to sub in the mean values that I had from my table before. So V equals 40, K equals 60. So like that. So that means this point should be 2,400. Yep, and that should be the peak flow value. And just the extra note is that this point is like the tip of the parabola, right? So that's going to be actually in the middle here. So actually I can label what these points should be. That would literally just be in the middle of these 2 points. And you can see how when speed equals 40, density equals 60. So those are like equivalent. Okay? So what you can just do is sub in the middle of the, or what if I say sub, find the apex of the parabola. And that's how you find the peak flow. Okay, and then that should pretty much be question B. So we found the free flow speed, jam density, critical density, and maximum flow. And then and then these two are the other 2 parabola graphs. These 2 questions would be to write the parabola equations as shown here. I'm pretty sure if you just do that, that should answer the question. The parabola, which is going to be, like these ones. Okay, and then, yeah. Yep. Okay. So I'll move on to trip distribution. Okay, so it says the northern region of Sydney has 4 areas, and then we have some information. So we're given the expected future travel times. So this gives us like how many minutes it's going to take us to travel from like 1 to 1, or 1 to 2, 1 to 3, 1 to 4, and they give us every single combination possible, basically. Now, just keep in mind, like, if it says from zone 1 to zone 1, and there's a number, it's like saying, like, imagine if, like, how long does it take for you to travel from like Kensington to Randwick? Like, they're still encompassed in the same zone area, but you still have to travel from one point to another. So that's what it's saying is taking 9 minutes. And then, yeah. So this one is going to be equivalent to Tij, which we will see later. And then here they give us the expected productions and attractions. So this is like basically the total number of people that they're expecting will leave each zone and arrive at each zone. Okay, so part A says, using the following calibrated function, what is the travel time in minutes applying the gravity model of the form Vij equals Pij, and then that. And then the question is to determine the trips generated from zone 1. So what this question means is basically we're going to find how many trips were generated from zone 1 to zone 1, and then from zone 1 to zone 2, and then from zone 1 to zone 3, and then from zone 1 to zone 4. So we have to basically apply this equation 4 times. And this is the equation for the gravity model. So now I'm just going to write down what each of these mean. So Vij, that's the number of trips that go from zone 1 to zone 2, or from zone I to zone J, whatever is specified. And then Pij PI, that's the number of productions that come out of I. So how many people are leaving zone I? And then AJ is how many people are arriving at zone A. So, yeah. And then now what is FIJ? So that's going to come from, as they say in the question, it says it's equal to ATIJB, where A equals 100 and B equals -1, and that basically means it's going to be this to the power of -1, which is equivalent to like this. So it's basically 100 over Tij. So that means that's equal to 100 over the time it takes to go from I to J. And we get this value from this first table here. Like that. Okay, so that's where we're getting that. And then our PI and AJ is going to come from this table here, the second one. Okay, so in order to find the number of trips generated from zone 1, so like I said, it's wanting us to find V1, 1, V1, 2, V1, 3, and V1, 4. So going from zone 1 to each zone separately. So let's start with the first equation, which is finding V from zone 1 to zone 1. So firstly, I need PI, which is the productions from zone 1. Hang on. So this is equal to P1 times A1 Okay, so P1 is the productions that come from zone 1. So that value is actually given to us in the table here. So it says productions from zone 1 is 2,200. Okay, and then I have to find A1, and that's going to be attractions to zone 1, which is given by 2,800. And then lastly, F11. So like I said, that's equal to 100 over the time taken from zone 1 to zone 1. So that is given here. From zone 1 to zone 1, that's going to take 9 minutes. So I'm going to sub in 9 here. And then now I have to find the sum of all of the attraction spots. So basically what I'm going to do is, firstly, A1 is the same as the numerator, right? Because we just used A1 and F11. And then to find A2, that's going to be attractions to zone 2, and I'm going to just move along this row. And then for the top one, from zone 1 to zone 2, that's going to take 20 minutes. Next for attraction 3, attractions to zone 3. So as you can see, I'm literally just moving along the box like this. And for zone 1 to 3, that's taking 10 minutes. And then lastly for zone 4, as you can see, if I move along the boxes, I should get this value. So basically this is for when j equals 1, this is for when j equals 2, this is for when j equals 3, this is for j equals 4. Okay, so if you put that in the calculator, that should give you something like this. Oops, 914.1872. Okay, and obviously, sorry, and this number corresponds to the number of trips that were produced from zone 1 to 1. So I'm going to round this off to the nearest number. Were made, so that means 914 trips were made from zone 1 to zone 1. Okay, so That's awesome. And now I have to basically repeat for all 4 zones. So I'll just show you repeating to the second zone. So V12 equals okay, like that. So now, obviously this might seem repetitive, right, if I have to do the same equation 4 times, but you'll see that it's actually not that hard because it kind of overlaps. So firstly, let me find P2, right, productions to zone 2, and that's going to be this one here, 3,200. But then after that, I need to find A2 times F12, but that's actually going to be the same as this set right here. So where I already subbed in j equals 2 and found the same thing. So actually now all I have to do is change the numerator to the second like kind of set down here that was originally in the numerator. But if that's confusing, you can just literally find it again from the table. So I'm literally just going to copy this like this. Oops. Okay, sure, like that, right? And then if you calculate that, that should give you around 514.23 trips. Okay, so basically you repeat this for all 4, and all you have to do is change each of these to the numerator each time. And then your final answer is going to be, basically you could just compile all of these. So from zone 1 to zone 1, we found that there should be 914 trips generated. From zone 1 to zone 2, there was 514. And then you should find them for zone 3 and zone 4. If you want to check my answers, you can look at the PDF document with these notes that I've sent out. But I'm just not going to go through them in this video because it's like the same thing and I'm tired. So yeah, hopefully that's all good. Yep, and then this will just be the answer like this. Okay, and then for question B, it says, okay, they like changed the formula basically. They changed this so that A equals 100 and B equals -3. And then you have to do the same thing. So literally, the question's exactly the same. The only thing that changes is I have to do it for where B equals -3. So that's equivalent to doing this. So Tij to the power of 3 on fraction, which is 100 over the time it takes from I to j, and then cubed. So obviously your friction factor is going to be different, but then after that, you literally just repeat the question for all 4, like from zone 1 to zone 4. Okay. Next, I have the horizontal alignment question. So there are some values that I can take from the question straight off. So I've got the grade equals 6%. I've got the speed, which is 100. I've got the cross slope, which is 1.5. Now remember, cross slope means the slope of the lanes themselves. So like, you know how it's only shaped in like a crown shape? It's the angle of that crown shape. So like this angle here. So if the road was like this is C right here. Whereas the slope of the actual road itself driving upwards, this is the super elevation. Wait, I mean grade. Sorry, that's the grade. Grade, cross slope, and then super elevation is only for when it's like a banked curve. Okay. Okay, and then super elevation is 8%, and side friction is 0.12. Awesome sauce. Now look at my diagram. This is basically what we're working with. You're on like a rocky plain, and the road is like sloping upwards, but also curving around. Yeah. And there is a wall in the way. So if it says there's a rock wall, what's the main thing about this that you need to keep note of? Is that you can't see around the corner. So like if my car is like here, right? Like I can't see past this wall, right? Like I can't see what object is here. So how thick the wall is gonna affect my stopping side distance, which will come into play later. And then it also told us that the lanes are 4 meters wide and the shoulder is 3 meters. So like this. Okay, and then it says determine the radius of horizontal curves. Okay, so I need to find the radius. So to find the radius, I'm going to try firstly to use this radius formula because I have the values for everything. I have V, I have E, and F. So if I try and sub those in, I should get R equals 393.7 meters, and obviously because like in transport you just need to find an answer that works. It doesn't have to be like an exact answer, so I'm going to round up to 395 meters, and that's my guess as to how big the radius should be. But then actually if you look at table 7.6, which is here, minimum radiuses that you should have for these speeds, for 100 k's an hour, it says 100 k's an hour and super elevation is 7%. You should have a minimum radius of 414 meters. So actually, we can't take 375. I need to take the bigger one. So I'm going to take the radius as 415 meters. I'm just rounding up slightly so it's easier. Okay, so now that's my guess at the radius, and now I need to check if this radius is okay in terms of stopping distance. So I'm going to calculate stopping distance. And remember, stopping distance is how long you have how far you can see basically, depending on your obstacle. So I'm gonna draw a top view of this road. So it's curved like this. That's the center of the road, and then I've got the 4 lanes either side. Oops. Like this. And then there is a wall in the way, which I'm gonna draw like this. And then now let me just fill in some measurements. So the radius from the center of the circle to the center line of the road, that's going to be radius equals 415 meters. And then for this formula, I need to find RV, which is the distance from center of circle to the middle of the inside lane. So what that means is I'm going from the center of the circle here all the way to the middle of the inside lane, which is here. Now note that there's 2 lanes on each side, right? So if I split this up further, there's 2 lanes on either side, and then from this lane I'm going from the middle of the closer lane to the middle, and then going to the center like this. So if I look on the diagram, that's going to be equivalent to the center of the circle here all the way to the middle of that inside lane, like this. And that's going to be RV. Okay. So then, and then I need to find M as well. So M is the distance from the wall to the middle of the inside lane as well. So that's going to be from here. Oops. Yeah, from the middle to the edge of this wall here, which is M. And that's actually going to be the same as from this wall to this point as well. And that's going to be 3 plus 4 divided by 2, which is 2 meters. So 2 plus 3 equals 5. Oh, sorry, and RV is going to be 415 minus 4 meters minus 2 meters. So that will be 409 meters. Okay, so then oops. I'm subbing in those numbers, and I should get 128.04 meters. Now I need to check, basically, is this enough distance of seeing the object to be able to stop in time? So in order to figure that out, I need to calculate the stopping side distance. So, well, a formula we are familiar with. So all of these values I got from the question itself. So the reaction time, speed, D factor, I'm taking 0.46 because on the standards, that's what it is for mountainous roads. When typically we use D equals 0.36, right? But this one I'm using 0.46. And then the gradient I'm going to take as -6. I'm taking -6 because it's harder to stop faster when you're going downhill, right? So I'm taking the worst case scenario. What's the stopping distance when I'm going downhill and it's even harder for me to stop? So, okay, imagine I sub that all in. I should get 167.87 meters. And now, remember, my stopping distance was 128. So, it's saying that I physically need 167 meters to make sure I can stop in time. But the minimum distance I can, first see an object is 128 meters, right? So that's not good. I could crash. So stopping distance is less than stopping side distance, so it's bad. You don't have enough time to stop, so not okay. So what I'm going to have to do is, this radius needs to increase. Radius. So what I will do is, what should I increase the radius to? So right now it's 415 meters. Let me increase it to a really random number. R equals 720 meters. Okay, so if I sub in those same values back in, RV again is going to be 720 minus 6, and M is still going to be 5. And if I sub those values in, I'm going to get stopping distance as 169 meters, and SSD, I'll actually see that in the formula, none of the variables change, right? The speed hasn't changed, the reaction time hasn't changed, the grade hasn't changed. So actually, it stays the same. So 167 compared to 169, that means I can stop in time now. So that is tick OK. So that means this radius is valid. I'm going to keep my radius as 720 meters. And would you need a spiral curve? No, you wouldn't, because you need a spiral curve if the radius is greater than 500, as you can see from table 7.3. Okay, now the second question is, it says that the radius has a requirement that it has to be less than 500 meters, right? But right now, we just said we want our radius to be 720 meters. So obviously, we need to change something like the road to make our radius reduce to 500 meters. So how can we reduce the radius? There's a couple of things we can do. Firstly, we can reduce speed, or we can increase the road shoulder. So let's start with reduce speed first. So what we're going to do is, firstly, the new radius has to be at least 500 meters or less. And then I'm going to find stopping distance again. So if radius is 500, this is 500 minus 6. Why am I doing minus 6? It's because, remember, for RV, I need to find the distance from the center of the circle to the center of the middle lane. And the center of the middle lane is 6 meters away from the center line. So um, 494 and M still equals to 5. So S, if you sub that in, you should get 689 meters. So let's test what the value of stopping side distance will be with these new decreased speeds. So instead of 100 km an hour, what if we try 80 km an hour? Then the SSD will be 118.55, and then this is going to be less than the stopping distance. So since it's less, it's going to be a valid road. So actually what you should do is check for if the V is 90 km an hour. So go from 100, 90, see if it works, and then go down to 80. And you should find that that's the first one at which the stopping sight distance is less than the sight distance. Yep, so that means if we make the road radius of 500 and speed equals 80 km an hour, then this road will satisfy. Now another way we can make this road safe is increase the road shoulder, because remember in our question there's like a rock wall in the way, and that's what's kind of reducing our sight distance. So if we change the shoulder, maybe we can see faster and then like be able to stop faster. So what we're trying to do is increase this little bit here, which is the shoulder of the road. So in order to do that, I'm going to sub in R equals 500, V equals 100 km an hour. So I'm not reducing the speed this time, but I'm focusing on the shoulder. My SSD should be like that. And then what I'm going to do basically is sub this in to, oops, actually this should be so speed equals 494 and I don't know what M is yet, right? Because I don't know what my shoulder is. So actually, since that's the only variable, and make side distance equal to stopping side distance, so that's the best case scenario, and that should give me M equals 8 meters. So then that means my shoulder should be 8 meters minus 2 meters, because like that 8 meters is equal to M, and M is equal to from the wall to the middle of the inside lane, right? And the inside lane already takes up 2 of those meters. So if I subtract 2, then the remainder part should be how much shoulder I should have. So I should have a 6 meter shoulder here, but since my shoulder is already 3 meters, right? So all I have to do is increase the shoulder by another 3 meters. So what I'm going to do is already a 3 meter shoulder. So excavate 3 meters of the wall, like 3 more meters of the wall. So they're gonna have to like dig out the mountain, so it's like flatter basically. So then you should be able to see the road more clearly, and then people could stop in time if they see something on the road, and then they can not crash. Okay, so that's the 2 methods you can use to reduce the speed. To reduce the radius on the road. You can increase the road shoulder or reduce the speed. And I've supported it with calculations. Whoops. Okay, let me just like quickly rub this out. Sorry, forgot to do that. Okay, and then I can explain this from scratch. Okay, cool. So now this is an Earthworks question from week 10, which I don't think we actually did in the tutes. So yep. So okay, basically all of your Earthworks questions, you're gonna get them in this format. So there's gonna be a bunch of like cross sections like this, and you get a bunch of numbers like this. So how you should think of this is they're giving you the cross section at regular points along the road. So imagine there's like a road like this, right? And then each of these diagrams is a cross section like this. So every 100 meters they took a cross section, and then they've drawn it for you here. Okay, so for Earthworks questions, it's quite straightforward actually. You just have to memorize the steps basically. So firstly, our first step should be, if the question info changes from cut to fill or fill to cut, then find the distance where it transitioned. So that sounds complicated, but basically what that means is in the question they will always give you like fill equals and cut equals areas like this. So what it means is you need to find the 2 adjacent ones that have a cut and then don't have a cut anymore, or have a fill and then don't have a fill anymore. So in that case what I mean is this cut here, on the first diagram there's a cut value, but on the second graph there's no cut, right? So there was a transition, meaning it's like this. There's like a cut volume like this, and then it decreases, and then becomes a fill volume as you go on. And that happened in between these 2 points on the road. So we need to figure out where it stopped being a cut part and then started becoming a fill part. So how to do this, all I have to do is draw these 2 triangles like this. So this is the cut value, the fill, and I'm basically drawing, this point represents the 400 meter chainage, and this part represents the 500 meter chainage. And then I'm going to label this as x, which is like a distance, like the distance from 400 chainage where it transitions. And then since the cross sections are 100 meters apart, I'm going to do 100 minus x for the other side. And then I'm going to label these height values as well. And where do these height values come from? They come from these numbers here, which are like on top of each other. Okay, so now how do I find the value of x? I need to basically use similar oops, similar, I have to use similar triangles. But don't worry about like thinking about the theory too much. It's always going to be this same diagram, this same format. So all you have to do is x over 1.3 equals 100 minus x over 0.8. So kind of using the ones that are adjacent to each other. And then basically if you solve this, you should get x equals 61 meters. So that means the cut stops somewhere 61 meters along. Okay. And then looking at the rest of the fill and cut values, you'll see there's also a change from 600 to 700, right? There was a fill and then there's no longer a fill anymore. So a transition happened there as well. So again, I'm going to draw some triangles like this. So fill, cut. This is 600 meter chainage, 700 meter chainage, and then this transition happened x, somewhere x along, and then the heights of these are 2.3 and 2.4, and I got those from here because they are like on the same line as each other. So again, I'm going to use like that, and if you solve for x, you should get 49 meters. So that means this is 49 and this is 51, and I'm going to use this information soon. Okay, so I've done my pre-graph work, and now I basically need to copy this entire graph. So they have this in the lecture slides as well. Literally just copy the exact table. Like, I know it looks really long, but literally just copy it like word for word because you need all the information here. So in order to fill this out, I've also just written some steps here, like how to fill an Earthworks table. If you just follow these steps one by one, then you will be able to find the answer. Again, like all you have to do is remember how to do these steps, and then the actual calculation is very straightforward. So firstly, I'm going to fill in the chainage points here. Very easy. So, and I'm going to write this in the smaller, thinner boxes, like this. Okay, and then step 2, I'm going to find the fill distance. So for how many meters was fill happening in each, between each point. So, like from my diagram, from 400 to 500, for how long was fill happening? So actually there was fill happening for the entire duration. How do I know that? Because there's fill area to start with, and then by the time you finish, there's still fill area. So that means fill was happening for the whole time. So I'm going to put fill distance is 100 meters here. Now notice how in the step I put fill distance and cut distance as separate steps, because don't try and combine fill distance and cut distance together, because fill distance and cut distance can happen at the same time. So it's not going to add up to 100 all the time. So I kind of treat them separately. Try and do all of the fill distances first and then all of the cut distances. Okay, so then from 500 to 600, here, okay, there's again fill and fill again. So fill still happened for 100 meters. Okay, and then from 600 to 700, so there was fill to start with, and then there's no longer fill, right? And that's why we did that transition calculation here. So that means the fill should be happening for 49 meters before it stops. So that means I'm going to fill in 49 here. And then lastly, there's no fill at 700 and then no fill at 800. So there's just 0 meters of fill in that region. Okay, now I'm going to do the same thing for cut. So remember, like I said, cut distance and fill distance don't necessarily add up to 100. I just have to literally base it off of these words that they give me on the side here. So firstly, it starts with cut, but then on the second picture there's no cut, right? So again, that's where we found that transition distance. So cut should have happened for 61 meters. And then same thing, I'm gonna look at it and then see if the cut, see the distance for which the cut was happening. Okay, then step 4, it says fill area and cut area, which is given in the question. So what that means is I'm literally going to take these numbers now, like the area numbers that they've given us in the question, and then fill them all out in this column and this column. So if I do that real quick, that should give me like this, and I'm going to write those in the skinny boxes. Wait, no. Okay, like that. Okay, and then step 5, now I need to find the double area. Now just note, double area doesn't mean 2 times of the area, it means adding the area from the top box and the bottom box and then writing in the middle. So basically I'm going to take this top area number and this bottom area number and then add them together. So like that, and then I'm going to do that for all of these. So 20 and 35 gives me 55, 35 and 0 give me 35, and then 0, and so on, like this, for cut and fill. Okay, and then number 6, now I need to find the volume. So what I'm going to do is I'm going to take that double area I just found, divide it by 2, and then multiply it by the fill or cut distance. So what that means is, firstly I'm going to take this double area, which is 25, divided by 2, and then multiply it by the fill distance. So since this is the fill column, I'm going to take the fill distance here, so I'm going to multiply it by 100. Okay, and then same thing here, I take the 55, divide it by 2, and then multiply it by the fill distance, like so. Now the only change is when I have the fill distance be anything that's not equal to the distance between the 2 changes. So in this case, if the fill distance is not 100, then there was a transition, right? And if there was a transition, I actually can't divide by 2, I have to divide by 3. And then I still multiply by the distance. So only in the case where the distance is not equal to 100, then I'm going to divide by 3. And in this case it's just 0. So again, for the cut volume, I'm taking 18 divided by 3 this time instead of 2 because my cut distance is less than 100. Same for 40 divided by 3. But then this time, I'm going to do 80 divided by 2 because my cut distance is 100 meters, which is the entire distance. Okay, so then that's actually the whole table filled in, and then now I can find the net volume. So I'm going to find the net fill and then net cut. And if I add those up, I should get something like this. My numbers might be slightly off because I didn't check properly with the calculator, but it should be somewhere around there. So then to find net volume, what I'm going to do is the fill minus the cut, or the cut minus the fill, whatever is bigger. But the only thing with the cut volume is that in the question, it told us that the Earthworks has 10% reduction in volume. So actually I have to basically reduce this by 10%. And I'm going to do that by multiplying by 90%. And I only do that to the cut volume because only the stuff that you dig up is going to reduce in volume, not the stuff where there's already a hole to fill in. Like the hole is not going to reduce volume. It's the soil that you dug up that's reducing in volume, not the hole. So yeah, and then that should give me like 21 meters cubed. So and since we subtracted the fill volume, I have 21 meters cubed extra soil. Cool. And that should be the answer to the question. Any questions? Do you think I could hear you? Joking. Okay. Hopefully that was helpful. That's the end of the paper. If you have any questions about this one, like I'm happy to try and answer it. Yeah, if you just message me or something. But if you have any like super technical questions, like why is this like this or something, like you might be better off asking Divya because she knows like the exact rules. Or like if you have a question like, oh, well, how should I write this in the exam or something like that, Divya can probably help you best. But I can try help you like look at the question. So yeah, okay. Thanks guys. Goodbye.